Hey everybody, welcome to our third and final video solution to quiz 6. And here we're going to be doing what we want to be doing all along, which is solving differential equations. So we have an initial value problem, and we're going to solve it using the Laplace transform. So note, we have actually seems like quite reasonable. It's a nice little first order differential equation. The forcing function is a little bit wonky. It starts off as cosine of t, and then it's going to dip by 3 when you get to pi. Okay, and then we also have this initial condition that the value of the function y at 0 is equal to 8. All right, we'll see if that makes much of a difference. So we're going to start by applying the Laplace transform. And we know that if you take the Laplace transform of a derivative, you get s times the Laplace transform of the function minus the initial value of the function at 0. There we go. That's why we need this y of 0 equals 8. So when I apply L to both sides, and note, I have to do it to both sides, not just the left, I get S L times the Laplace of y minus y of 0, which we know is equal to 8, plus 4 times the Laplace transform of y. And then, okay, on the right-hand side, I need first the Laplace transform of cosine of t. All right, well, we can go to our table, and we see the Laplace transform of cosine of t is s over s squared plus 1. Then we need minus 3 times the Laplace transform of the unit step function at pi. And again, our Laplace transform table tells us it's going to be e to the negative pi s over s. All right, well, we want to solve for L of y. And let's see, I get Ly times, I have an s, a plus 4. And let me just toss this, well, this was a minus 8, and I'll put an 8 on the other side. So I have 8 plus s over s squared plus 1 minus 3 e to the negative pi s over s. Again, I'm trying to solve for L of y, so I'm going to divide by s plus 4. So Ly is equal to 8 over s plus 4 plus s over, okay, I have s plus 4 times s squared plus 1 minus, okay, I'm going to rewrite this just a little bit because we're not going to be able to do partial fractions with the exponential up here, so I'm just going to pull that out to the front. So e to the negative pi s will come out, and I'm left with over here a 1 over s times s plus 4. Okay, because remember, I have to divide everything by this s plus 4. Okay, well, let's see. I don't want to put this all together. That just feels bad. Instead, I want to split this apart. I want to split this apart as much as I can. And so there's going to be two opportunities to use the method of partial fractions here. This second one is going to be pretty easy because it's all just distinct linear factors. So this bit here I can rewrite as something over s plus something over s plus 4. To get the s, I cover up this s and make s equal to 0, so 1 over 4. And to get the coefficient over s plus 4, I make this s equal to negative 4, right? The root of s plus 4. So I get 1 over negative 4, or negative a fourth. All right, so that was the easy one. This one here, I'm going to break this up as something over s plus 4 and something over s squared plus 1. Now again, the s plus 4 coefficient, that's going to be easy. I just cover it up and then make all my s's negative 4. So I'm going to get negative 4 over, let's see, 4 squared plus 1 is 17. Whoops, I put it on the wrong one though, didn't I? Yep, negative 4 over 17. All right, now what's going to go on top here? Well, it's going to have to be some linear term. So let's call it like bs plus c. And we better do a little side work. So I want to take s over s plus 4 times s squared plus 1 and rewrite it as something over s plus 4. Actually, we know it's negative 4 over 17 plus bs plus c over s squared plus 1. Okay, I clear denominators. So I get s is equal to negative 4 over 17 times s squared plus 1 plus this linear piece, bs plus c, times s plus 4. And my goal is to find the b and the c. Well, let's look at the s squared terms. There's none of them on the left. And on the right, I have, let's see, negative 4/17 s squared. And then I get bs times s, so plus a b. Ah, excellent. B has to equal 4/17. All right, now to get my c, I'm going to look at the constant term. So there's no constant term on the left. And on the right, let's see, I get negative 4/17 times 1. So again, negative 4/17. And then c times 4, so plus 4c. So 4c is equal to 4/17, and c is equal to 1/17. Excellent. So we're going to come back up here, and I can replace my b with 4/17 and my c with 1/17. Now, for the purposes of taking Laplace transforms, or in this case, inverse Laplace transforms, everything looks pretty good except for this term here. That's pretty gnarly. So I'm going to break this up just a little bit more. First, let me pull this 4/17 to the front and write this as s over s squared plus 1. Then I have this other bit. I'm going to pull the 1/17 to the front and just have 1 over s squared plus 1. Okay. So now I can go to my table and take the inverse Laplace transform. And I'm going to get y equals, all right, so this 8 over s plus 4. The 8 is just some constant, so I'm really looking at 1 over s plus 4, and that comes when you take the Laplace transform of e to the negative 4t. All right, then we have this next bit, this negative 4/17 over s plus 4. Well, that's going to be minus 4/17, and the same thing. It's just 1 over s plus 4, so e to the negative 4t. Hey, I bet I'll be able to combine those if I want. Okay, then I move over. Here I have 4/17, and s over s squared plus 1, that's the Laplace transform of the cosine. So this is cosine of t plus 1/17. Then I have 1 over s squared plus 1. That's just the Laplace transform of the sine. Okay, then I have minus 3. Oh, okay, so this one is a little bit trickier looking, right? So to finish this off, let's take this last piece, bring it up over here. So I have minus 3 e to the negative pi s, and then let's see, I have a fourth over s. So let me just make this fourth come over here, but then I have this over s. Then I have the second piece. Well, again, negative 3, now it'll be times negative a fourth. It'll be plus 3 over 4, e to the negative pi s over s plus 4. Okay, this piece here is the Laplace transform of negative 3 over 4 times, well, this is actually a really nice, easy one from the table. This is u pi of t. What about this one? Ooh, okay, so this one is almost u pi of t, except there's this shift. There's this shift in there. It's a shift by, well, okay, instead of an s, you have an s plus 4. So what did our second shifting theorem tell us specifically? Let's write that down. All right, our second shifting theorem said that the Laplace transform of the shift of a function times the unit step function at that shifting point is equal to the decaying exponential, right, with the same shifting point in the exponent, times the Laplace transform of f. Now, we're actually needing to read this from right to left. We have this decaying exponential, and the c, right, the c is equal to pi. And then you have 1 over s plus 4, all right? So this is, I could rewrite this as 3 over 4 e to the negative pi s times the Laplace transform of e to the negative 4t. So if I read this backward, what am I going to need? Well, the 3/4 is just gonna be in there, right? I don't have to worry so much about that. All right. If I have e to the negative pi s, okay, that's what I have here, then I'm going to get a shifting function, right? So this a u pi of t. And then, since I'm taking the Laplace transform of e to the negative 4t, that's my f. So I need e to the negative 4, but not t minus pi. So e to the negative 4 t minus pi. Okay, so that's what we needed. So now we can finish off our y. We're just going to copy this information. So we have minus 3 over 4 u pi of t plus 3 over 4 e to the negative 4 t minus pi u pi of t. And yeah, right, we can combine some things if we want. Right, these first two terms are going to be able to be combined. Look, I can factor out a u pi and even a 3/4. Okay, I'll leave that to you. All right, well, there we go. We solved a differential equation. It wasn't trivial. We used integration by partial, or rather, not integration, but partial fractions method. All right, lots of stuff getting combined in here. First shifting theorem, second shifting theorem. We got it all working for us.